Alright, let's go. Number 10. If a magnetar came within 1,000 kilometers of you, it would kill you before you could see it. And not by radiation, or by explosion, or by any of the ways you might imagine. It would kill you by pulling apart the atoms of your body, one by one, using magnetism alone. A magnetar is a type of neutron star, the ultra-dense corpse left behind when a massive star explodes as a supernova. But magnetars are not ordinary neutron stars. They have the strongest magnetic fields ever measured in the universe. So strong that the numbers involved almost stop making sense. Earth has a magnetic field. It is what makes compasses work, and what deflects the solar wind, and what protects life on the surface. That field has a strength of about half a Gauss. A refrigerator magnet has a field of roughly 100 Gauss. A powerful MRI machine, the most powerful magnetic device most humans will ever encounter, can reach about 30,000 Gauss. These are the magnetic fields we live with, and use, and consider strong. A magnetar's magnetic field can reach 1,000 trillion Gauss. That number is so far beyond anything in human experience that comparisons stop being useful. It is a magnetic field so intense that if a magnetar existed halfway between the Earth and the Moon, it would erase the magnetic strips on every credit card on Earth. If it approached within 1,000 kilometers of you, the field would be so strong that the electrons in the atoms of your body would be forced into extreme, distorted orbits. Chemistry itself would break down. Your atoms would deform, your molecules would fall apart, and you would cease to exist as a biological entity, not because of heat or radiation or force, but because the very rules of atomic structure would have been rewritten around you. You would die of magnetism. In a way, no human has ever died. In a way, no human is designed to comprehend. Number 9. The surface of a magnetar can crack open, and when it does, it releases more energy in a fraction of a second than our sun produces in 100,000 years. Magnetars, like all neutron stars, have a crust, a thin, incredibly rigid shell of impossibly dense material wrapped around a strange, super dense interior. And that crust is under constant, unimaginable stress from the magnetic field, twisting and pulling on it from within. Occasionally that stress becomes too much, the crust cracks, and when it does, an event occurs that has no equal anywhere else in the known universe. It is called a starquake. A starquake on a magnetar is not like an earthquake. It is not a shifting of tectonic plates. It is a catastrophic release of magnetic energy, triggered when the crust suddenly fails and the entire configuration of the magnetic field snaps into a new state. And the amount of energy released is, quite literally, cosmic. In 2004, we observed a magnetar called SGR 1806-20, located about 50,000 light-years from Earth, on the other side of our galaxy, produced a starquake so violent that it released more energy in 1/10 of a second than the sun will release in over 100,000 years. Think about that. In the time it takes to blink, a single object released more raw energy than our star produces in 100,000 years of steady burning. The pulse crossed our galaxy at the speed of light, arrived at Earth, and, from a distance of 50,000 light-years away, it briefly compressed and ionized the upper atmosphere of our planet. It disturbed our ionosphere. It affected satellites in orbit. From the other side of the galaxy, a starquake on a single tiny neutron star physically affected the atmosphere of Earth. If that same event had occurred within just a few light-years of us, it could have severely damaged our ozone layer, potentially triggering a mass extinction. A Magnetar starquake is not a local event, it is a cosmic one, and the energy it can release in a single instant dwarfs almost anything else in the universe. Number 8. 1 teaspoon of magnetar material weighs more than every human on Earth, combined, times 1,000,000. Magnetars, like all neutron stars, are made of a substance called neutron degenerate matter. It is what you get when the gravity of a collapsing star crushes ordinary matter so hard that the electrons are forced into the protons, forming a soup of pure neutrons packed so tightly that quantum mechanics itself is the only thing preventing further collapse. The density of this material is almost beyond comprehension. A single teaspoon of neutron star material would weigh approximately 1 billion tons. Some estimates go higher, into the trillions. Let that sink in. 1 teaspoon, a tiny amount, the kind of measurement you use for sugar in your morning tea, and it would weigh more than the combined mass of every human being on Earth, many, many times over. It would weigh as much as a small mountain. If you tried to place that teaspoon on the ground, it would not sit there. It would punch through the crust of the planet, fall through Earth's mantle, and continue toward the core, pulled by its own overwhelming density, unable to be stopped by anything less dense than itself. You cannot hold a piece of a magnetar. You cannot even come near it. The density is so extreme that ordinary matter simply cannot exist in its presence. Everything else, in comparison to magnetar material, is essentially empty space, and an entire star, roughly the mass of our sun, is compressed into a sphere just a few kilometers wide, made of this impossible substance. That is what a magnetar is. A world-sized piece of density that should not, by any intuition, be able to exist, and there are dozens of them drifting through our galaxy right now. Number 7. Magnetars spin thousands of times per minute, and the ground beneath their equator is moving at a significant fraction of the speed of light. When a massive star collapses to form a neutron star, something spectacular happens to its rotation. The star, which was slowly spinning as a giant, suddenly finds itself compressed into a tiny sphere. And just like a figure skater who pulls in her arms and speeds up, the rotation accelerates enormously. Some neutron stars end up spinning hundreds of times per second. Some spin over 1,000 times per second. Now think about what that means for magnetars, which are neutron stars roughly 10 to 20 kilometers across, rotating at these unimaginable speeds. The surface at the equator is moving at an appreciable fraction of the speed of light. The ground itself, if you can call it ground, is racing through space faster than any human-made object has ever moved. And this rotation is not gentle. Combined with the crushing gravity and the extreme magnetic field, the surface of a magnetar is a place where the fundamental laws of physics behave in ways we do not fully understand. Space near the magnetar is distorted. Time itself passes at a different rate close to the surface compared to far away. If you could somehow hover just above the surface of a magnetar and survive, you would experience time dilation so extreme that seconds for you would be minutes for the rest of the universe. You would be riding a piece of dead matter, spinning at nearly the speed of light, wrapped in a magnetic field strong enough to erase atoms, watching time slow down around you. Nothing you have ever experienced would prepare you for the reality of standing near a magnetar. It is a place where every rule of the physical world you were born into ceases to apply. Number 6. Sansei. Some of the strangest signals we detect from deep space, called fast radio bursts, may come from magnetars, and we have almost no idea what is triggering them. For years, one of the deepest mysteries in astronomy has been a phenomenon called a fast radio burst, powerful, millisecond-long pulses of radio energy arriving on Earth from deep in the cosmos, seemingly at random. Each one carries an enormous amount of energy, packed into a burst so brief that we can barely even measure it. Where do they come from? For a long time, we did not know. Some scientists speculated about advanced civilizations, some suggested exotic cosmic events, but in 2020, evidence began to mount that at least some fast radio bursts come from magnetars. That is startling in itself, because it means these millisecond-long, incredibly powerful signals arriving from across the universe are triggered by objects that are, from our perspective, deeply mysterious. But the deeper puzzle is what specifically is causing them. Why do magnetars produce these bursts? What is triggering them exactly? And why do some magnetars produce them repeatedly, while others fire just once and go silent? We still do not fully know. The physics of fast radio bursts is still being worked out. What is clear is that magnetars, when they release these bursts, are producing signals so bright that we can detect them from billions of light years away. Some of the fast radio bursts we have detected originated in galaxies so distant that the light left them when Earth was young, and they arrive at our radio telescopes, decoded from noise, as tiny, powerful, mysterious pulses of energy from dying stars in unimaginably distant places. Every day, our telescopes pick up more of them, and every one of them is a magnetar, somewhere in the universe, doing something that even the physicists studying it cannot fully explain. Number 5. Magnetars are extremely rare, and yet the ones we detect suggest millions may be hiding in the darkness. Astronomers have currently cataloged only about 30 confirmed magnetars in our entire galaxy. 30 out of hundreds of billions of stars. They seem from that number to be exceedingly rare. But this number is deeply misleading, because magnetars have a short active lifetime. They only remain observable and detectable for a few tens of thousands of years after they form. After that, their magnetic fields decay, their emissions fade, and they become almost impossible to spot. They become dark, silent, invisible. Which means that for every active magnetar we can see, there are almost certainly enormous numbers of dead ones. Ancient magnetars, whose magnetic fields have faded, drifting silently through the galaxy, invisible to our instruments. Some estimates suggest that the total number of magnetars, active and dead, in our galaxy could be in the tens of millions, perhaps more. Think about that. tens of millions of these objects, scattered through our galaxy, most of them dead and silent, most of them impossible to see. The Milky Way is filled with them, ancient, dark, ultra-dense corpses, each one containing more mass than our sun, each one wrapped in the faded remnants of what was once the strongest magnetic field in the universe. And you cannot detect them. They are not shining. They are not pulsing. They are just there, drifting, silent, buried in the dark, and every one of them is a tiny package of impossible physics, waiting, in most cases forever, to reveal itself to no one. Number 4. A magnetar in our solar system would rewrite reality, and it is not impossible. We have talked about how magnetars affect the Earth from thousands of light years away. But what would happen if one entered our solar system? The magnetic field would begin distorting the sun, the planets, and the space around us long before it ever reached us. As it drew closer, its magnetism would begin to interfere with electronics, communications, and eventually the fundamental structure of matter itself. Well before it arrived at Earth, its presence would trigger geomagnetic chaos on our planet on a scale that has never been recorded in human history. Auroras across the entire sky, not just at the poles, massive interference with all electrical systems, the failure of every electronic device connected to a power grid, and that would be from a distance. If it came closer, if it entered the inner solar system, the effects on Earth would go from disruptive to catastrophic. The magnetic field alone could begin to affect biological processes. The behavior of enzymes and chemical reactions in cells depends on the electromagnetic environment. Introduce a field strong enough, close enough, and biology itself begins to malfunction. Cells would die, bodies would fail. Life on Earth would collapse, not from radiation or heat, but from the sheer intensity of the magnetism warping the chemistry of everything alive. And here is the deeply uncomfortable point. This is not impossible. There could be a dead, drifting, silent magnetar somewhere out in interstellar space, invisible to our instruments, heading in our general direction. We would not necessarily see it coming until it was extremely close, and by then, it would be far too late to do anything at all. Number 3. Magnetars distort space and time in ways that push against the laws of physics themselves. We have talked about how a magnetar's magnetic field can distort atoms, and how its rotation causes time dilation, but the effects go deeper still. In the space immediately around a magnetar, the sheer intensity of the magnetic field creates conditions that challenge the fundamental laws of physics. According to quantum electrodynamics, the theory that describes how light interacts with matter and electromagnetic fields, extremely strong magnetic fields can begin to affect the properties of empty space itself. In the space around a magnetar, the vacuum can become birefringent, meaning it splits light into different polarizations in a way that ordinarily only happens in specific crystals. Empty space around a magnetar starts to behave like a strange, exotic optical material. This is not just a mathematical curiosity. It is a real, observable effect that has been detected in the light from these objects. Photons of light passing through the space near a magnetar are altered by the presence of the field, in ways predicted by quantum theory decades ago, but only recently confirmed. The vacuum itself, the empty space we take for granted, is being reshaped by the presence of the magnetar, which means that near a magnetar, empty space is not empty. It is a strange, warped, electromagnetically active medium. Light behaves differently there. Matter behaves differently there. The very rules of reality, at the deepest level, are being modified by the presence of this single, incredibly compact object. Magnetars are not just extreme objects existing in the universe. They are, in a very real sense, objects that bend the universe around them and force reality to behave in ways it never does anywhere else. Number 2. The first fast radio burst ever detected from within our own galaxy came from a magnetar, and it briefly outshone entire galaxies of stars. In 2020, astronomers made a discovery that changed our understanding of fast radio bursts. For the first time, they detected one coming from within our own Milky Way galaxy, from a magnetar known as SGR 193 5+2-154. And what they observed was staggering. The burst was, from a cosmic perspective, relatively brief and moderate, but for that fraction of a second, a single magnetar in our own galaxy produced a burst of radio energy so intense that if we had detected it coming from another galaxy, we would have classified it as a fast radio burst, which meant, for the first time, that we had a confirmed source. A specific identified object, producing a signal that had puzzled us for over a decade. But think about what that observation revealed. In an instant, a single magnetar, tucked away in our own galaxy, briefly released, in radio waves alone, a level of energy that could be detected from across the observable universe. That is what these objects are capable of. In a fraction of a second, they can broadcast louder than entire galaxies of stars in the specific narrow band of radio waves, and they are doing this throughout the universe, all the time, every day. Somewhere, magnetars are firing. Somewhere, their signals are traveling across billions of light years. Somewhere, our telescopes are picking up the faint whispers of magnetar activity from the depths of the cosmos. Each one is a reminder that these objects, however small and dense and rare, are among the loudest, most violent, and most powerful things in the entire universe. Number 1. Magnetars are, quite possibly, the most extreme physical objects that can exist in reality. And we barely understand them at all. Let us put it all together, because the full weight of what a magnetar is only becomes clear when you see the complete picture. They are the ultra-dense corpses of dead stars, compressed into spheres just kilometers across, containing more mass than the sun. They spin thousands of times per minute, at speeds approaching the speed of light. They possess the strongest magnetic fields ever detected anywhere, so extreme that they distort empty space, deform atoms, and could destroy your body from 1,000 kilometers away. They can produce starquakes that release more energy in a fraction of a second than the sun produces in 100,000 years. They fire off millisecond-long radio bursts that we detect from across the universe. And there are tens of millions of them, most of them silent and dark, hidden throughout our galaxy. And here is the deepest, most disturbing truth. We do not fully understand any of it. The mechanisms behind their extreme magnetic fields are still debated. The physics of their starquakes is still being worked out. The exact triggers of their fast radio bursts are still unknown. We know these objects exist, we know they are extreme beyond imagining, but the details of how they work, why they behave the way they do, and what is possible for them to become remain some of the deepest open questions in astrophysics. Every time we look closely at a magnetar, we find something new that we did not expect. Every measurement pushes the limits of what we thought possible. Every observation reveals another layer of extreme, exotic, beyond experience physics that our theories struggle to describe. And that senior astronomer, the one some of you have asked me about, the one who allegedly said, off the record, that he wished we had never looked. When he said it, magnetars were part of what he meant, because these objects represent a kind of upper limit, a ceiling on how extreme reality can get. They are the point at which the universe itself seems to push against the very edge of what our physics can describe. And once you truly understand them, once you grasp what they are, you realize that our universe is not the calm, orderly place we like.